All right, in this section, we're going to take a look at logarithmic functions. We spent some time talking about the exponential functions in the last section. Those were functions like, for example, do some work in the margin up here, like y equals 2 to the x, right? The base is constant, and the variable is in the exponent. Right, so we take this constant base and we say, what are the output? What kind of outputs do we get? What are the y values we get if I just play around with the exponent, if I let that value change? Once we know what these exponential functions are, now we can actually define the logarithmic function, which is just what we describe as being the inverse of the exponential function. It's like the backwards function or the undoing function for the exponential function. And so here's what I mean sort of more precisely by that. The way we define the log function can be given in this equation. We would say that y is equal to log base b of x if and only if you take your base b and you raise it to the y power, it gives you the stuff inside. If and only if x is equal to b to the y. So there is, just like we have an exponential function of a given base, right? We fix a base and then we look at that exponential function. We do the same thing with the logarithmic functions. We have a log base b, a log base, some positive constant that's not 1, right? Just like with the exponentials. Any exponential equation can be written in a logarithmic form. Every logarithmic equation can be written in an exponential form using that definition. So, one thing to kind of keep in mind with logs is that logs, their purpose in life, the reason they can get up in the morning every day, the thing they do is that they spit out exponents. That is their reason for existing. With the exponential functions, I'm actually going to go back to this graph that we made in the last section here. So if I take a look, say, at this point, right? If we look at the black graph in general, all right, the way we got that was that we put in different values of x and we saw what happened to y. So I know that, like, if I look at that highlighted value right there, that point on the graph, that tells me that 2 to the third power is equal to 8, right? With the logarithmic function, we're going backwards. I'm saying, what if I tell you the y-coordinate? What if I tell you, I want to know when the 2 to the x function takes on the value 8? And can you tell me the exponent I'd have to put on 2 to get that? That's what the log function does, is it tells you the exponent you need. So we're going to get some practice working with the log functions, using this definition to rewrite a log function in an exponential form and vice versa, and solve some problems. So in example 5.4, here's an exponential function equation, y is equal to 2 to the x. We want to write that in the logarithmic form. Now, we're just going to use this equation up here, that correspondence. So if y is equal to 2 to the x, that means, now I need the log form, so this is log base something of something else equals something. There's 3 blanks we got to fill in, right? So the base of the log is the same as the base of the exponential. So that's 2. Logs spit out the exponent. Well, here's the exponent right there. The exponent is x, so that's what goes on the other side, and that leaves y as what goes inside. 2 raised to the x power gives you y. I'm going to clean this up a little bit. Log 2 of y equals x. There's your logarithmic form. We're going to evaluate each of these. We could do all of these basically without a calculator because they're convenient numbers, right? So we're going to find log base 2 of 8. So the first thing I'm going to do is say, let's call this x so that we really want to find the value of x. And then we will write the exponential form. So if log base 2 of 8 is equal to x, that means that if I take my base 2 and I raise it to the x power, I get 8. Well, what power do I put on 2 to get 8? Again, these are convenient numbers, so I don't need a calculator. That is x equals 3. And so that means that log base 2 of 8 is equal to 3. Next, we want to find log base 4 of 1/4. Well, again, let's take the same approach. We're going to call it x. And if I write the exponential form, I'm going to take my base 4. 4 raised to the x power is equal to 1/4. And, 1 over 4, that's, 1 over 4 to the first, that's 4 to the negative 1. So that means the only way this happens is if x is equal to negative 1. And there's our value, log base 4 of 1/4 is equal to negative 1. Next, log base 64 of 4. So, again, logs spit out exponents, right? What we want is the power that we have to put on 64. So 64 to the x power is equal to 4. Now, I did say all of these can be done without a calculator because they're convenient, but we do have to kind of think about, we have to think about it in the right way, I guess. So, if I think about how 4 is related to 64 in an exponential sense, we could note that 4 cubed is equal to 64. And so that means that the cube root of 64 is equal to 4. And that means that x is 1/3. That's the 1/3 power is the cube root. And so finally we get our result here. Log base 64 of 4 is equal to 1/3. All right, let's try another one. We could use a similar technique to solve a lot of different kinds of problems that just involve, finding some missing piece of a logarithmic equation or a missing piece of an exponential equation for that matter, I guess. Here we're going to solve for b, and we're going to start just by rewriting the log function in its sort of sister form, the exponential form. So might take my base b, I raise it to the negative 4 power. Remember that logs spit out the exponent, and that gives me 1 over 81. So now I just need to solve this equation. I guess there's a couple of different algebraic routes we could take, but I'm going to rewrite the left side here as 1 over b to the 4th is equal to 1 over 81. And if 1 over 81 is equal to 1 over b to the 4th, then it must be the case that b to the 4th power is equal to 81. And if I know what b to the 4th is and I want to find the value of b, well, I'm going to take the 4th root. And we get b equals 3. Now, you might be thinking, we're looking at an even root of a positive number, and shouldn't there be, 2 of those roots, right? I mean, 3 to the 4th power is 81, but negative 3 to the 4th power is also 81. And we know that we're just looking for positive 3 because a base is always positive. Okay. In this next example, we're going to rearrange this equation to solve it for t. So we got p is equal to 75 times e raised to the negative 0.005t. Now we're not going to get like an actual value, numerical value for t, because we got 2 unknowns in this equation. Hopefully you recognize we have our new number e showing up, right? That's the natural base. But what we want to do is solve this equation for t, and note that t is trapped up here as an exponent. And we're going to find, in general, that any time we're trying to solve for something that's trapped up as an exponent on some base, we're going to use logs to help us with that. So the first thing I'm going to do here is divide both sides by 75, because what I really want to isolate the exponential part, right? So I want to get rid of that coefficient in front, so I have p over 75 is equal to e raised to the negative 0.005t. And now I have it written in the basic exponential form. A base to a power equals, in this case, the fraction p over 75. Now I'm going to use that definition of the log to rewrite this. So remember, the way that goes is that log base b of x equals y if and only if b to the y equals x. So my base on the exponential is e. That means that I'm looking at the log base e. The log always spits out the exponent. So on this side I'm going to have negative 0.005t, and then inside I'm taking log base e of p over 75. Now we're almost done. We want to solve for t, so we're just going to divide both sides by negative 0.005. And if you take the calculator and find 1 over negative 0.005, you get negative 200. So this is really negative 200 times log base e of p over 75. That's equal to t. If you've worked with logs before, you might already know that when we're working with the log base e, we give it a special name. We're going to talk more explicitly about this in a little bit. But if you see log base e, or if you find yourself wanting to write log base e, we usually write that as ln, and that stands for the natural log. So whenever you see ln, it means the log base e. Alright, next we're going to learn some properties of logs. Logs are really just one of my favorite things to work with, mostly because we have these really nice properties. A lot of ways we can simplify, either split up or condense logs to kind of help us solve problems. So the first two properties here are really similar. They just tell us what to do if we're either multiplying or dividing inside a log. The first property says, well, if I'm multiplying inside the log here, I'm going to split that up as adding two logs. They have to be the same base, right? They're all the same base throughout. Or if I am dividing inside the log, that turns into the subtraction of two logs. It's important to note that these properties work in both directions. So I could use it to split up a log where I'm multiplying or dividing inside. Or if I'm adding logs, I can use it to condense those logs and write as a single log of a product. Or if I'm subtracting logs, I could write it as a single log of a quotient. And then this one here is probably my favorite property that tells us that if we are raising the argument inside to a power, so I've got log base b of x to the r, and I could take that exponent, bring it down in front as a factor in front of the log. So these are what we would call arithmetic properties, how we kind of rearrange the algebra of the logs themselves. And then we have basically some properties that come right from the definition of the log and how they're related to the exponents. The first one says log base b of 1 is 0. Well, if we just write out what that means in the exponential form, you're going to agree with it right away. So this log base b of 1 equals 0, the exponential form is b to the 0 equals 1. And we already know that. If you raise a non-zero base to the 0 power, you get 1. The next one, log base b of b equals 1. Well, let's write that out in its exponential form. That would be our base b to the first power is equal to b. And I don't think anybody's going to disagree with that. And then last, log base b of b to the n is equal to n. Let's write this out in its exponential form. You take your base b and you raise it to the n power, and it gives you the stuff inside. B to the n equals b to the n. So that hopefully that makes sense. We don't take any issue with that equation. So we're going to get some practice using these properties. Log base 4 of 5/3. Well, I'm dividing inside this log, so that's log base 4 of 5 minus log base 4 of 3. That's about it. It's about as far as we can go. Now for this next one, we've got log base 5 of x squared y over z. So the first thing I see is that I've got this division, right? I've got a fraction inside. So I'm going to split that up using subtraction as subtraction of logs. So this is log base 5 of x squared times y minus log base 5 of z. Now this first log, right, there's a product inside, so I'm going to use that first property. It says I can split that up as a sum of logs. So we get log base 5 of x squared plus log base 5 of y minus log base 5 of z. And now we can use that third property that says, look, if I am raising something to a power, if I'm raising the argument to a power inside the log, I can bring that power down as a factor in front. So this is 2 log base 5 of x plus log base 5 of y minus log base 5 of z. There's a couple things I want us to observe right here. First, that the argument inside involved multiplication and division. And once we were done kind of splitting it up, the factors up top correspond to these positive logs. And any factor in the bottom, well, that corresponds to a negative log. Second, you might right off have noticed that we had this square on x inside, right? And maybe you were thinking about that third property. Oh, I've got a exponent. I know I can bring that down in front. And it's good to observe that and key in on it right away, but we have to know that we cannot apply that until we got to this point here, because it has to be the whole argument that's raised to that power, right? I was not allowed to bring that 2 down in front right away until I kind of had it isolated in that that first log right here on this line. Okay, now we're going to go the other way. We want to write each of these as a single log, so note that the bases are the same. Log base 2. If you're going to combine logs and write them as a single log, you got to have them as the same base, log of the same base. So these bases are the same. We're adding them. That means we can write it as with multiplication inside a single log. So this is log base 2 of 3 times x. Similarly, the part B, the base is the same. It's both 2. We're subtracting this time, so that means when we combine them, we're going to divide inside the log. We get log base 2 of 5 over x. And last, here I've got 3 logs, all the same base. I'm doing some addition and subtraction. So just note that any negative log corresponds to this factor ending up in the denominator. So we could do this in a couple of steps. In fact, we actually need to do this in a couple of steps, I guess. When we're condensing as a single log, one of the things we want to observe right away or deal with sooner than later is factors in front, right? I've got a 2 times log base 2. All the other coefficients are 1 or negative 1. But here I've got this factor 2, so I actually want to deal with that first. Bring that 2 up as a power on x. So now this is log base 2 of 3 plus log base 2 of x squared minus log base 2 of y. And now I can use the fact that positive logs correspond to factors up top, negative logs correspond to factors in the bottom. So this is log base 2 of 3 x squared all over y. Okay. Let's do some more simplifying. We're going to use these properties of logs, and let's see. So in the first one, in fact, in the first two, what we're going to use is the fact that here I've got a log base 3, and the base of the argument is also 3. Right? I've got log base 3 of 3 to the 14th. And property 6 here just tells me that's going to give me the exponent n. Now that should make sense, I hope. You know, logs spit out the exponent. So if I want to find log base 3 of 3 to the 14th, really what it's saying is, tell me what exponent I need, that's the question mark, so that I end up with, you know, with 3 to the 14th. You know, what's the exponent I need to put on 3 to get 3 to the 14th? The answer to that question has better be 14. Next, we have a really similar one. Log base e of e to the 2 pi. What exponent do I put on e to get e raised to the 2 pi power? Well, that's 2 pi. Log base 2 of 6. Now this one's different. 6 is not a power of 2, right? So it seems odd that, that it appears here. But I'm going to do this in a couple of steps here. 6 I'm going to write as 2 times 3. So we got log base 2 times 3. Now I've got a product. So I got log base 2 of 2 plus log base 2 of 3. And log base 2 of 2, well, I can rewrite that. What power do I put on 2 to get 2? The answer to that question is 1. And then 1 plus log base 2 of 3. And then last, log base 7, oh, not quite last, we have 2 more, I guess. Next to last, part D, log base 7 of the square root of 7. I'm going to rewrite that square root of 7 as 7 to the 1/2 power. Log base 7, 7 to the 1/2. I'm going to use that same property we've been using, right? The base of the log is the same as the base of the exponential inside, so this is going to give me 1/2. And now we got one more here in this group of examples. Log base 5 of 1 over 25. Now there's a couple ways we can do this. I'm going to show you both ways. One is just to say, well, 1 over 25, that's the same as 25 to the negative 1. And in fact, 25 to the negative 1, you know, 25 is 5 squared. So this would be log base 5 of 5 to the minus 2. And now I've got the bases agreeing, log base 5 of 5 raised to the negative 2 power, and that gives me negative 2. Another way to think about this, I guess I'd say there's 3 ways. I'll say, let's see, the middle way, I'm going to go from this step here. And say I've got this minus 2 power, or this minus 1 power, so I could bring that up, bring that out as a factor in front. Negative log base 5 of 25. And what power do you put on 5 to get 25? Well, that's 2. 5 squared is 25, so you get negative 2 that way. Another way to think about this is to say that log base 5 of 1 over 25, well, I've got that's a fraction. I'm dividing inside. I could split that up as 2 logs. Log base 5 of 1 minus log base 5 of 25. Log base 5 of 1 is 0, right? That says what's the power I put on 5 to get 1. And of course that's got to be 0. Minus log base 5 of 25, and log base 5 of 25 is 2, so you get 0 minus 2, which is negative 2. So multiple ways to think about how to do that one. Now we're going to take a few minutes and talk about 2 common, or bases, you know, 2 very common bases. One, in fact, we call the common base, and the other is the natural base, right? We are already familiar with the natural base e when we were talking about the exponential functions. When we use that natural base on a log function, we call that the natural log. So that's what we got going on right here. So if instead of writing, say, log base e of 45, we would just write ln of 45. It's absolutely okay to write log base e if you want to write it that way, but you should definitely know and be familiar with the fact that if you see ln, that means the log base e. The common log is the log base 10, and it's in a lot of books they'll write the log base 10 without any base at all. So if you see log 45 and there's no base indicated, it is understood to be the log base 10. These bases are so common. In fact, they're built into our calculator, the TI-84. They're built into any basic scientific calculator. A lot of calculators won't have logs of other bases, so we're going to focus on making sure that we know how to rearrange things and be able to use the common log or the natural log to solve our problems when we start solving equations. So we're going to start, or I guess we're going to just get used to where these are located on the calculator and just do a couple of examples where we evaluate them. So here we can see where these buttons are located. If it says log, that means the log base 10. We have an ln button. That's the natural log. We need the calculator for a lot of things. So far we've done a lot of things with convenient numbers, right? I think we evaluated log base 2 of 8 by hand, right? We could say, oh, log base 2 of 8 is 3 because I know 2 cubed is equal to 3. But if they said find log base 2 of 9, we'd have a harder time. The best we could do is say, well, it's probably a little more than 3, right? Because 9 is a little more than 8. Our calculators, though, can evaluate the common log or the natural log. And here we're going to first start with log of 478. So I'm just going to hit the log button, 478. I get 2.6794. Now I can check this, I can convince myself. This is the log base 10, so if I wanted to verify, that means that if I take 10 and I raise it to the 2.6794, that should give me something very close to 478. $477.97. So really quite close there. And then, let's see, next we were going to find ln of 0.703. So we're going to use the natural log button. And I get negative 0.3524. And I could check that, right? That means that if I take e and I raise it to the negative 0.3524, I should get 0.703 or something very, very close to that. So second ln gives me the e to the stuff function. So negative 0.3524. And I get 0.702998886. So 0.7030 if I'm using 4 significant digits. All right, this next example is a problem that I put in the category of party trick mathematics. The common log is really useful in helping us rewrite very, very large numbers. So you might recall back in chapter 2, we had a section on exponents and we looked at scientific notation. We said, oh, well, scientific notation is really convenient if we're talking about numbers that are either crazy small or super huge, right? So when we work with numbers that are very, very large, we can run into problems on the calculator because the numbers are just too big for our calculators to handle, and they'll throw an error. For example, we want to evaluate the number 1024 raised to the 256th power and write it in scientific notation. So if I try to just do this on the calculator, 1024 raised to the 256th power, I get an error, overflow. The number's too big. There's not enough memory on the calculator to deal with it. But here's what we're going to do. I'm going to take this number, I'm going to call it n, so we want to know what n is. And I'm going to take the common log. It's really important that we're using the log base 10 here. Using a log of a different base won't work. So log n is equal to log of 1024 to the 256th power. And I'm going to use properties of logs, right? The reason we would take an equation that has no logs and impose logs on it is because we want to take advantage of those properties. So I'm going to bring that 256 down in front. So 256 log 1024. And right now, a really nice thing about the number 256 times log of 1024 is that we can plug that into the calculator without getting an error. So that's what I'm going to do. In the calculator, let's see, 256 times log 1024. And I get this decimal. Now, I'm going to write this number, and I'm not leaving out any digits. This is an example of a problem where I don't want to do any rounding at all until I get to the end. So I'm writing out all these digits. So 770.63678889, right? So I'm just writing out all the digits my calculator will show me. And this is equal to log of n. So I know what log n is equal to. What I want is n. So now what I'm going to do is take this equation and write it in the exponential form. So this is the log base 10. So if log base 10 of n is equal to this number, that means that n is equal to 10 raised to the 770.63678889. And now I'm going to take a few steps, each of which I think you'll agree with. First, I'm going to rewrite the exponent. Instead of 770.63678889, I'm going to write that as 0.63678889 plus 770. I'm basically just sort of splitting up the integer and fraction part, but writing that fraction part first. Now notice here I'm adding inside the exponent, and if I'm adding inside the exponent, I know I can write that as a multiplication. This is 10 to the 0.63678889 times 10 to the 770. And now I'm going to use the calculator one more time to evaluate 10 raised to the 0.63678889. And only here am I going to do any rounding, right? So I'm going to take it out. I guess I'll use maybe 4 significant digits, so 4.333 times 10 to the 770. That's our value of n. That is 1024 to the 256th power. And that's in scientific notation. So I know the first few digits of this number, 4333, and I know how big it is, times 10 to the 770. So if I were able to write out all the digits, I'd have to move that decimal point 770 spaces to the right. All right, so we're going to finish this section by talking about the change of base formula. I never remember, I usually don't remember the change of base formula. There's actually no need to memorize it if you know techniques for solving logarithmic or exponential equations, and which we're going to learn and which we need to know anyway. So, the change of base formula is down here in Theorem 6. It just says if I have a log, an expression written as a log of some base b, and I want to change it to a different base a, I can do that using this formula. So log base b of x is equal to the fraction log base a of x over log base a of b. So log base a of x, and then you divide by log base a of the old base. But we don't necessarily need to have that formula, we don't need to have it memorized or anything. And we're gonna see how we can arrive at that by going through this problem. So first it says let's evaluate log base 5 of 56. It says first set it equal to x and then write the equation in exponential form. So alright, I'm going to take x equals log base 5 of 56. And x is what I want to find. So I guess I assume in like decimal form, right? I just want to evaluate it. And I don't have a log base 5 function on the calculator to use. So I'm going to write this in exponential form. That means 5 to the x is equal to 56. Now, at this point, we have a choice that we can make. If I want to write out the value of x and I want to do it in, get an approximation, that means I want to write it out using either a log base 10 or the natural log, because those are functions I have on my calculator. So what I'm going to do here is I'm going to take the log of both sides. In fact, I think this time I'll take the ln of both sides. It really doesn't matter which one you pick. So I've got ln of 5 to the x equals ln of 56. And now the only reason to impose a log on an equation is to be able to take advantage of those properties. I'm going to drag that x down in front. X ln 5 is equal to ln 56. And now all we need to do is divide by ln 5. Ln 5 is just a number, right? Ln 5 is a constant. It is the exponent we have to put on e to get 5. It's a constant like any other constant. It's just sort of couched inside this ln. And so I know that x, as an exact figure with the natural log, is ln of 56 divided by a ln of 5. And now we can evaluate this in the calculator. Ln 56. I'm going to make sure I close those parentheses before I divide by ln 5, and then close those parentheses. I get 2.501 approximately. That's x, right? And that is what we were looking for. That's equal to log base 5 of 56. And I can check, right? If this is accurate, that means that if I take 5 and raise it to the 2.501, it should give me something very close to 56. And we get 5.66. Whoops, hold on. I did that wrong. 5 to the 2.501. 2.501. There we go, 55.99. So there's our check. This is the same, this fraction right here, that's exactly what we would get if we used the change of base formula and decided to write it as a base e.